Hi everyone, my name is Cosse, and I'm here to give you the lead for the gas turbine experiment. I've heard it many times today, so bear with me. This is a picture diagram of what the gas turbine looks like. Your air is going to enter here, go through the compressor, and then it's going to combust with the fuel, and then exit through the turbine and exit through the conversion nozzle. I'm going to give you a little introduction with the history, go into the theory of performance. Then I'm going to get into the experimental procedure and go over some results and graphs from the calculations. Frank Whittle and Hans von Ohain were the two people that are credited with the invention of the gas turbine engine. They were working separately and not together, and they did this without knowing. They kind of knew of each other, but they weren't working together. Frank Whittle, he received his patent in 1930, and Ohain received his in 1936. However, Ohain was the first to get his jet engine into flight in 39 compared to 41. A jet engine is essentially a gas turbine. They supply high thrust by accelerating air, and this utilizes the Brayton cycle, which basically you have air come into the compressor, it's combined with fuel, where it undergoes combustion, and then after combustion it turns the turbine, which produces work out and exhaust gases. This is the diagram right here, the pressure and the temperature entropy diagrams. Performance. They have a much higher thrust to weight ratio compared to propellers that were used in the earlier planes. The efficiency also is based off of the fuel consumption. And then the specific thrust is the output thrust divided by the mass flow rate. We're going to get into that calculation. We're going to find the velocity due to the thrust. And then higher pressures and higher temperatures, it's a great thing. We can get better efficiency, but we also sacrifice cost because we need to have materials that are able to withstand these higher temperatures and higher pressures. The main thing with this experiment, I'm not sure if it's working, you have to have eye and ear protection. It's going to be very loud. The procedure will be located above the gas turbine. Once again, wear eye and ear protection is very loud. We're going to need to record the initial load cell readings, and then the recorder is going to be asked to record the pressure, temperature, fuel mass flow rate, and thrust data between 40,000 and 80,000 RPM at increments of 10,000. 5 additional readings should also be taken at your lower speeds, just so you can kind of get your mass flow rate when it's just starting up. These were the calculations I used. Mass flow rate was rho VA, or density, times velocity times my area. This was the velocity exiting the nozzle with the thrust. That's my mass flow rate times velocity. And then if you need to calculate the fraction of energy released or the work of the compressor or turbine, these are the equations that will also be used by the reporter. For results, these were the given results that were on the Google Docs. It was given to me in PSI, my different pressures at different part locations of the gas turbine, and I was going off of the RPM speed of the turbine. I was also given fuel flow in gallons per hour. I hate working with the English units. I kind of went back and forth converting with metric and all. It was a pain. And then what I was asked to do as the lead was I was given to come up with the velocity, and I calculated in inches per second. It's kind of hard to understand, I guess. And I feel like I got it a little bit off because I calculated my density of air was off. And also too, I feel like the mass flow rate, you have your mass flow of air coming into the compressor, but you also have that fuel being injected, and that will add to that mass flow and kind of mess it up a little bit. So it's not the same mass flow throughout the gas turbine. We're given our RPM, and then we're asked to find the velocity using 3 different methods, using the MDOT method, using our thrust, and then using our pressure calculations. And these are all 4 different scenarios at different RPMs of the turbine blade, and we're calculating the velocity at the throat, or the exit nozzle, sorry, I found. And then we go to our graphs. I was also asked to graph the fuel calibration curves, 1 and 2. One is based on RPM, and then and one is based on MV. I did not have a zero value, so I kind of found the average differences between these and went down so I could get a zero, so I could have a little bit kind of a slope so you can see what it's like to start up. It was also asked to plot those values that I found earlier. So this is the velocity with respect to indot, velocity with respect to pressure, and velocity with respect to thrust. These are my RPM of the turbine, and then this is the velocity in inches per second over here. So in conclusion, gas turbines allow us to achieve better performance than propellers. They operate using the Brayton cycle, and the performance can be quantified by using the efficiency and specific thrust. Some of my calculations I did. Does anyone have any questions?